Yeah, welcome to our first QCA meeting of the semester. We're the Quantum Computing Association. So if you're looking for the Classical Computing Association, you're in the wrong room. So yeah, let's get started. So this is our leadership team. You guys want to come up and introduce ourselves? So I'll introduce myself. I'm Resmit. I'm the president for QCA this semester. I'm a physics and math third year undergraduate student.
I'm Fee. I'm a third year electrical engineering student.
I'm Elisa. I'm a fourth year computer science student.
I'm Noah, and I'm a second year math.
So yeah, if you ever have like questions about stuff, we're all on the Discord. You can message us, and make sure you join the Discord, by the way. But yeah, you can always ask any of us if you have questions at any point in time. So yeah, great. So what is Quantum Computing Association? So we're Georgia Tech's undergraduate and graduate quantum computing club. And also if you're like not a student at all, anyone is welcome to join our meetings. We don't have any like applications. There's no like fee that you have to pay, nothing like that. So you should come to our meetings whenever you're available and yeah, have fun. So yeah, we focus on quantum information and quantum computing. So I'll talk a bit more about what that is in a bit in case you're new to the field. But we work on projects, review papers, write our own papers now. And then we hopefully will have lectures and talks from speakers that work in quantum computing, both in industry and academia. And yeah, so last semester we started doing workshops as well for the first time. So if you're new to quantum computing and you want to learn like the theory and how you apply it to do your own things, we primarily use Qiskit. So if you want to learn how to use Qiskit, which is the predominant quantum computing tool, we will help you learn that. And also one of our heavy focuses is quantum error correction. So I'll talk about the project a bit later, but we're also doing quantum hardware this semester, hopefully. So we're going to be putting together a proposal to do quantum hardware. And so if you want to help with that, then definitely keep in touch with how that's going. But you don't need to have any experience to join, so don't worry about that. So yeah, like, how do you explain quantum computing? So if you're not familiar, classical computers use typically voltages to represent information. So if you have, you have like a circuit and it has different channels running through it, each channel can be at a high voltage or a low voltage. And the voltage being high or low tells you whether it's 0 or 1. That's a discrete difference. In a quantum computer, you use qubits instead of classical bits or just bits. And these qubits are quantum mechanical, so they come with a lot of special quantum mechanical properties. So for example, if you have an atom that has different energy levels that you learn from chemistry, it can be in multiple energy levels at the same time. And you can probe that transition using lasers and microwaves and things like that. Or if you're using a superconducting circuit, it can have current, and that current can have anharmonic discrete energy levels. And the energy levels of that circuit, of that superconducting qubit, are the qubit levels. So just like this drawing, you have 0 and 1, like a classical bit, but you can also have a superposition of them. And you can have quantum entanglement, where it's not just like statistical, it is very strong physical correlations between qubits. And these properties that I briefly mentioned are what give quantum computing the power to hopefully speed up many different computational problems. So yeah, that's the general overview. Don't worry if you don't understand any of it or you don't have as much background in like the physics of it. We try to cater this to anyone from any background. And there's lots of ways that you can play into quantum computing, even if you're not, like a theoretical physicist or something. So there's this video. It's always here. I never know how long to play it for. I'll just talk over myself. This is a superconducting quantum computer. So like I mentioned, you can have chips that are really at the bottom of the sky, like somewhere down here. And that chip has circuits that can be in quantum states. So they can be in different energy levels at the same time. So that's an example of a quantum computer. So yeah, that's like an example of what the chip would look like. So Richard Feynman was really big into this stuff. If you're interested in like biology, chemistry, physics, math, optimization, business, finance applications, quantum computing poses a lot of potential solutions to solving problems in those fields a lot better than we can today. And so that's really one of the goals of quantum computing. So yeah, it's all based on this, like really complex quantum mechanics about like you have states that can be 0 and 1, but they can also be a continuous combination of 0 and 1. So like we'll often say like, oh yeah, this is a sphere that we call the Bloch sphere, and the Bloch sphere has a north pole, which is 0, and a south pole, which is 1. The classical bit will only be at the pole, or the quantum bit can be anywhere in between on the sphere. And so you have a lot more states in your space to explore, and you can store a lot more information that way. And yeah, entanglement. So if you have 2 qubits, you can correlate their states very strongly. This is an example of like what a quantum algorithm looks like. This is what we call a quantum circuit. It's basically like each of the horizontal wires that you see is a qubit's flow over time. So here they start out in some state, and then you apply these logical operations. So the logical operations in quantum computing are sort of similar to the ones that you have in classical computing. You can do like AND gates and NOT gates, those slightly differently, but we have our own other gates as well. So rotation gates, Hadamard gates, general unitary gates that we'll all talk about, and measurements. So one of the most like strange things about quantum mechanics is how measurements work. And this is a really important thing in quantum error correction that we think about a lot. And yeah, so that's like the quick overview. We'll talk more about like quantum computing, like scientifically, like technically next week when we host our quantum computing intro workshop. So if you want to like learn more of the details, definitely come to that. It'll be here, same time, same place. And yeah, like if you might have heard of some of these results on the news. So there's a company called QCA. They were started by professors at Harvard and MIT who do a lot of really high-tech quantum computing research. And they said, hey, we can commercialize this. So they do a ton of really cool work with many qubit quantum computers. So each of these green dots that you see here isn't just like a computer animation. These are actual physical atoms that are detected using cameras to detect photons that are being emitted by these atoms every like millisecond. So this is them actually moving, and you can see like sometimes they put them together to couple 2 atoms using lasers and things like that. So this is the sort of stuff that you can do with quantum computing. And then this is just an example of like the scaling of quantum computing. So people believe that as you have more and more qubits, like typical devices in like an academic lab will be usually under like 30 qubits, unless you're like Harvard or Caltech. But besides that, like many, the biggest quantum computers today, though, are around 100 to 200 qubits. So we're sort of like in this region at this point, and we hope that as we have more and more qubits, we'll be able to get more and more accurate results out of our quantum computers. So yeah, you'll see a lot of like news articles that say, oh, we reached quantum supremacy or quantum utility or quantum advantage. A lot of those claims end up getting disproven really quickly, because what ends up happening is a quantum computing research team will say, okay, we beat classical computers. And then a month later, a classical computing team will say, no, we just ran that same algorithm faster on our classical supercomputer. correction. They haven't fully shown it, is something I should say. A lot of this news will be like, oh, we detected this and that, but really they mean we detected traces or possibilities of this and that. But yeah, the general idea, am I screen sharing it right there? Okay, yeah, okay, sorry. Yeah, so the basic idea though, is you have these quantum bits and you say, okay, if I have 100 quantum bits, I can store 100 qubits worth of information. But if one qubit gets messed up, all the information that was stored in that qubit gets lost. And so what they hope to do with quantum error correction is store information in multiple qubits. So, if I were to come over, punch your quantum computer, and you lose one of your qubits, the other maybe like 6 or 7 qubits that are in that logical qubit will still hold the same information. And so that is what Google hopes to do with their Willow chip. Let me see if I. So yeah, our plan for the semester, like I said, hopefully we'll have speakers. Most of our meetings this semester will be focused on our project that I'll talk about in a bit, and then also workshops, like I mentioned. Let me see, do I have a separate, do I have a slide about the workshop? No, okay, so let me mention the workshop now. So for our workshop, what we'll be doing this semester, and we're open to like opinions or like what you guys are interested in seeing. But last semester, we had a intro to quantum computing workshop and an intro to QEC workshop. And that's what we will be doing again this semester. So next week, we'll do an intro to quantum computing, and we'll have another workshop, which is an intro to quantum error correction. And then during that workshop, we'll also discuss quantum algorithms. So last semester, we didn't do a workshop on quantum algorithms. This semester, we will be doing that. And then in addition to that, we're thinking of doing a workshop on quantum hardware, because I know a lot of you guys are like engineering majors and you're interested in like, how does quantum hardware work? Like what's the actual like technical details of what's going on? So we'll also be doing that at some point in the semester. But yeah, if there's other things like topics that you guys want to learn about in quantum computing, definitely let us know. I'm sure that we can find like either one of us or someone else at Georgia Tech who can talk about that field. So yeah, workshops are really just there to help you guys learn more about this field. And then yeah, project meetings are most of it. And then I guess like the next thing is like talking about the project. But before we get to that, I just want to say like the purpose of our club, like I mentioned at the beginning, is really to help everyone here get into quantum computing. So if there's anything that you would like to see, like, or like new project ideas or workshops or like materials or resources or anything like that about quantum computing, definitely let us know. I would say like, if you are interested in getting into quantum computing as a career, this is definitely one of the best places to like participate through our project that I'll talk about, because we've had a lot of, like graduate students and alumni who have gone to schools like Duke and UCSB for their PhDs and master's degrees in quantum computing. And we've had people who've gotten internships at places like Quantinuum and IBM, really big companies for quantum computing. So, if you want to get into a career in quantum computing, this is definitely one of the places to be. So yeah, our semester project that I've been talking about so much. So this project, I'll say like, we started out like 3 years ago as purely interested in saying, can we implement quantum error correction as described in one of the papers that came out around that time on our own? So we wanted to write our own quantum error correction implementation that we could run on simulations and or hardware. And over time, we've been able to do more and more with that. So we started out by just implementing hard-coded quantum error correction algorithms. But now more recently, starting like around last year, 2 years ago, we started becoming more interested in generalizing that. So not only now can we implement like individual quantum error correction algorithms, we're able to implement generalized quantum error correction algorithms across wide classes of code. So like stabilizer codes and Pauli stabilizer codes and things like that. And as of like last semester, really, what we've been moving towards even more is optimizing quantum error correction and using it to run algorithms. So yeah, so like I said, like that's a lot of words. Like you don't need to understand like what any of that means. But what we try to do with this project is teach each and every one of you what you need to be able to contribute in some way. We want everyone to be able to make a significant contribution to the project. So in any way, shape, or form that you would enjoy working on, we can always find resources that will guide you in the right direction. Usually what will happen is like every single person will have their own specific interests that they want to learn more about and work on. And we'll find resources that help you go in that direction. yeah, we'll talk about it more like throughout the semester, like different projects and project ideas that you can work on, but this is just the overview. So yeah, I guess I should probably say like a little bit more about quantum error correction. So I sort of said it before, but like this is a quantum computer that's just there to look pretty. But that on the right is an example of what a logical qubit is. So like I mentioned, if you have 100 qubits, physical qubits, you can store information on every single one of those qubits individually. But if one of those qubits gets lost, all this information is gone. So what we do is we entangle a number of qubits, like in this example, 7 qubits, in a very special way, so that, for example, if qubit 5 were to get lost, then qubits 2, 3, and 6 tell me about the information that would have been stored in qubit 5. Okay? And by storing this information across multiple states and spread in this non-localized manner, you're able to resist local errors, which is what most quantum errors end up being, a lot better. And so this is a very, like, whenever we have like speakers or like whenever I meet someone in quantum computing, I always like to ask them like, hey, do you think quantum error correction will ever become unnecessary? And the answer has never been no. Quantum error correction, unlike most things in quantum computing, is one of the things that we know is here to stay. We don't think that there's ever going to be a future without quantum error correction. And that's why we're so interested in working on it. So that's like the core, heart of our project. And from that, we stem out to other things. So yeah, what have we accomplished with this? So yeah, we started out with just basic proof of concept notebooks demonstrating error correction and hardware simulation. And then we've also written our own open source code base, which is, it's an open source Python library. You can install it yourself on your laptop. And we also published it in a software journal that allows you to do a wide class of quantum error correction simulations. And so yeah, we generalized this as much as we could, but we're still working on doing that further. And then optimizing quantum error correction. Quantum error correction is really, really expensive because what you're basically doing is every now and then you're looking at your quantum system, that lattice of 7 qubits, and you're saying, did an error occur? What error occurred, if so, and how do I correct it? And you have to do a lot of extra steps in addition to your computation. So you'll be running your computation, and every 5 seconds or every couple of milliseconds, you'll have to do this whole QC cycle. And if you have to do that too often, you're never going to finish your algorithm. If you spend 90% of your day doing QEC, you're never going to get anywhere with quantum computing. So one thing that we specifically are very interested in doing, which is actually very novel work that I haven't seen much of elsewhere, I can count on one hand how many papers have done this, but we're interested in optimizing how you schedule quantum error correction so that you can do it only when it's necessary and only when it's really necessary. And that should hopefully maximize your quantum efficiency. So yeah, that's just optimizing QEC. And then with these optimized QEC simulations, QEC algorithms, we're trying to run simulations now of actual physical systems using quantum computing. So for example, last semester, we did a lot of lattice stage theories from high energy physics, but we're also interested in condensed matter systems, biological systems, like neuroscience systems, chemistry systems. Anything that we can put on a quantum computer, we'll try it. So, if you're coming from more of a natural sciences background or an engineering or optimization background, and you're interested in solving problems with quantum algorithms, let us know. We would love to see more things run with our quantum error correction library. This is something that's been worked on for years. There's thousands of lines of code, and we really want to use it to do something useful. So if you have something you want to work on along those lines, definitely let us know. And yeah, one of our main results is just showing that using our code base, we can see an increase in fidelity between error-corrected results and ones that don't use error correction. So that shows that, we really are doing something that's meaningful. So that's the error correction project. We also have a hardware project. Do you want to talk about it, or I can?
Sure.
Sure.
Okay, yeah. So this semester, we also hope to start a new project, which would be an actual hardware project. And yeah, our goal is to just implement this actual quantum system. I think we were planning on using lasers, right?
Yeah, lasers.
So that we could perform certain universal gate operations or just fundamental operations using around 3 qubits, because that's probably realistically the we do. And this project is really good because you can learn, as Rav was saying earlier, there's many different ways you can actually realize a qubit. So you can learn one way that qubits can be realized, and then also how they're controlled and measured in practice. And then you can also like learn how very simple and fundamental quantum operations work. And then you can also get an idea in how things like superposition and entanglement play a role in how we make these measurements. So yeah, we still have to work on writing a proposal and getting a grant on this, but this is a project we hope to start this semester.
Any questions about this project or the other one? I think we have maybe a little bit more to say about the projects. Yeah, we'll have another set of slides if we have time going more into detail. Yeah.
The participation criteria to be part of a project.
None. Yeah, it's really like you get out of it however much you get in, however much you put in. You know, so we have some people who just want to like read papers and like look for ideas and suggest ideas and things like that. And you know, that's totally like great contribution, right? Like being able to like look at literature and say these are interesting things to work on or ideas to implement. That's like the most like basic level of being in the project. And then more advanced would definitely be like, you know, like writing proposals, writing code, running simulations. For the hardware, like setting up the hardware itself, if we can get the grants for it.
Could even be helping write grants.
Yeah, things like that. Because for the hardware project, we had an estimate last semester for how much it would cost. It's in the 4 digits, which is more money than the College of Computing has to give us. So we definitely need to work on getting funding. There's a couple sources, so like Unitary Foundation and some like Georgia Tech foundations that give funding to student organizations that we're pretty hopeful we can get a bit of money for. So, you know, we still have to apply to those though, and we have to get accepted. So figuring out like how can we convince them that this is something that they should give us money for is probably going to be the focus of this project for the next month, or a couple of weeks at least. Any other questions? One thing I should also say, like, I know we're early in the semester, so like later in the semester, people have like extra responsibilities or commitments. If this meeting time doesn't end up working for you, like we do most of our like collaboration like meetings at this time, but we also try to host extra meetings on other days of the week. So last semester we had extra Friday meetings that a lot more people could show up to. So if this meeting time doesn't always work for you, then check the Discord. We sent out a when to meet the like yesterday or the day before for the extra project meeting time. So definitely fill that out if you want to get involved in the project but can't always show up on Thursday. Great, thank you. Oh yeah, so I guess like this is just like a physical picture of like what we would be doing. So at the top, that's an example of like a quantum operation, a Hadamard gate. So this is one of the most important quantum gates. It puts your qubits in superposition. And this is an example of how you would implement it. You take lasers, each of these lines is light, and then you use mirrors to do rotations, and then you use wave plates to do phase shifts and general unitary shifts. And then at the very end, you detect the light, and based on the things like the polarization of the light, you can deduce from that what quantum information was stored in it. And so we're hoping to implement something like this. Problem is things like these mirrors, wave plates, lasers, detectors, they cost like hundreds of dollars a piece. So that's why we really need to get as much money as we can to put this together. Yeah. And yeah, so to get involved, we have our Discord, which is our main channel of communication. Make sure you're in that. We have our Google Drive where we have some resources. I will say our GitHub might be more, our Discord has other resources as well. So really you should just join this if you want to look for resources. Also our Engage link, if you can join that, I think like you're technically supposed to join that as an organization. There's nothing that's on the Engage page, but it's highly recommended that you join. I guess I can show really quickly. Does anyone need these QR codes right now? Yeah, I'll go for it.
I'll just take a picture.
Yeah, okay, sure. Yeah, but so our Google Drive, has stuff like what courses are useful, what careers are useful. Our weekly meeting slides will always be here, and any other like weekly resources will always be here, including past semesters. So if you want to see like past workshops or slides, this is the place to go. But most importantly for now, does anyone have any other questions about like that part? We have about 30 minutes left, so we figured that like for the rest of the time, we can answer questions, and then we also have some slides that we present to introduce the project, the QEC side of the project. So I'll go through this, but again, like if you have questions or anything, feel free to ask. So yeah, so what exactly are we doing in our project? I should maybe first link, if you go to github.com and then you search for logical Q, this is our repository. Hey, first result, that's great. This is our GitHub. So this is an open source Python package. So if you actually go to the PyPy repository, you can install it, pypy.com, logical Q. You can install this like any other Python package. That's not official. This is official. Yeah, so it's a Python library that lets you do a lot of quantum error correction stuff. So I think the documentation shows it a little bit, or yeah, so you can do things like creating logical circuits. So like before I showed you examples of quantum circuits, a logical circuit is basically a quantum circuit that uses qubits. And so you can do things like encoding and quantum operations and QC cycles and quantum error correction measurements, all stuff that we'll teach you guys, of course, in this library. And this is the reason this is interesting is because if you look at most quantum error correction like work that people do, there'll be libraries that require a lot of more work from the user. So for example, if you look at like a demo, a fragment demo of what a QEC code looks like when it's actually being implemented, there's a lot of code. You know, there's like magic looking numbers and a lot of mess that you have to code. But all of this is wrapped in, you know, just like 5 lines of code using our code base. That's why this is so powerful. Because now, if you want to go ahead and run a quantum algorithm like we have done using our library, you know, you just import our package like any other Python package, and then you code your quantum circuits just like this. You can visualize them, see what they look like, just like any other quantum circuit. And at the very end of the day, you can run them and get measurement results. And nowhere here did you have to think about QEC. So if you're interested in doing quantum algorithms, like I mentioned, but you aren't as interested in quantum error correction, you can code quantum algorithms in Qiskit like any other quantum circuit, import them into our library logical queue, and run them right away. We have interfaces for doing all of this stuff. So there's a lot of things that this can do. And our focus is really, well, our 2 foci are really 1, improving it to make it support even more, and 2, applying it to algorithms. So this is just an example of one of the high energy algorithms I mentioned. This is the Kogut-Susskind Hamiltonian that we implemented. And we want to implement more things like this. You know, there's chemistry models, like molecules that you can simulate. There's people who try to model like synaptic connections in the brain using qubits, things like that, all sorts of different things. And so any quantum algorithm, we want to try and run it, see what we can do. But yeah, our code base is entirely in Python. And so if you don't have any coding experience, that's good because Python's relatively easy to pick up compared to other languages like Fortran or Rust or whatever. So yeah, this is definitely like something that you can get into even if you haven't taken any computer science courses before. There's definitely a lot of code and it can be intimidating at first, you know, to go to like one of the like more complex pieces of the code and scroll through all of the lines of it. But usually when you're on the project, you'll focus on something specific. So, you know, we have people who focus just on like doing better measurements or doing better logical operations. And so then you get to focus on, you know, like a single function at a time, things like that. Yeah, I think like all the things this slide on that. Okay, yeah, so yeah, we have a code base, you know, you can import it in Python, user-friendly functions. It extends Qiskit, so anything you can do in Qiskit pretty much, you can do in logical circuit, which is really great. Seamless integration, so, you know, running algorithms is a lot easier than any existing library out there today. And then minimizing costs. So we have functions that do the things I mentioned before, like optimizing QC cycle scheduling. All those things are built into our library. And so if you want to get involved, like we have this because historically this is how we started, but it's really like a meaningless differentiation at this point. So we sort of split into theory and hardware. You don't need to have like a specific background to join either side of the project, but theory usually does more like implementing quantum error correction and software, things like that. Hardware is more running quantum algorithms and doing optimization, running things on hardware, because we actually are able to run our quantum circuits on hardware. We have access to Quantinuum hardware, IBM hardware, and hopefully more soon. IonQ hardware, QAra hardware. So yeah, we have access to a lot of hardware, like actual quantum computers that we can run on. So that's really exciting to be able to do. So yeah, theory, like I said, it's questions like how do you produce quantum circuits? How do you implement these gates? How do you perform more advanced procedures? If you're interested in any of these things, they're more like mathy, computer sciencey things like coding theory and information theory. This is probably like the sort of team you want to gravitate towards. Whereas if you're more interested in like, okay, how do I actually run a quantum algorithm? How do I port it to hardware? How do I do, like useful applications with it? Hardware is like more where you gravitate towards. Yeah, so we sort of have like different like task forces of people working on things. So I mentioned like we can do a really general class of quantum error correction algorithms using our code base. So we want to generalize this even further. Can we like abstract more and more parts of our functionality to be able to run more general algorithms? This is a lot better than hard coding things and having to recode things every single time you want to implement something new. So that's one big thing. Quantum information, if you're interested in more like the physics or math of quantum information theory, this is definitely like a lot of fun. You get to do a lot of like cool thing about math and Lie groups and Hamiltonians and commutations and traces and stuff like that, which makes some people happy. So yeah. Benchmarking, so this is like running things on hardware, telling like when you're doing quantum computing, there's certain numbers that you look at, fidelity, circuit depth, things like that. And it's a question of how do you actually benchmark all this stuff? We run all this code, but it's like, how do we know any of it is good or worth thinking about? We have to benchmark it. And so we need to put more effort into benchmarking our code base and benchmarking different logical implementations and algorithms to make sure that we're running things in an efficient and competitive manner to other research groups. QC cycle optimization, this is a project that we're like sort of trying to like wrap up at the moment, but there's still a lot of work to be done for it. The thing I mentioned before, like figuring out when should you do QEC in a quantum circuit and how do you optimize that? And lastly, just software. If you're interested in like computer science software, like programming things, there's a lot of stuff in our software stack that just needs to be improved. Even just like documenting things and writing test cases are a lot more important than they may seem at first. So yeah, point is, there's a lot to think about. These slides will be posted to the Discord and they're always in our Google Drive. So these are just like things that you should think about, like, am I interested in any of this? We'll talk about it more in the coming weeks as we have like workshops and project meetings. But the hope is everyone should be able to come to a point where you say, okay, I'm really interested in this question. And I'm going to spend the entire semester, or you don't have to fix like a project for an entire semester, but I'm going to spend a lot of time thinking about this question. You don't have to like do something that someone's already doing or do something that like we already have listed. If there's something new you want to do, we can totally accommodate that and figure out what the resources you need are. But that's sort of like why like I haven't really mentioned resources until now. Ignore these dates. Those need to be updated. We have some resources that we post, but really it comes down to, okay, there's a couple of resources in this flow chart. Again, this is linked, but there's a couple of resources here if you're like entirely new to things. But besides that, we give you all the resources you need for your project, depending on what exactly you're working on. Yeah, and like a point that we try to emphasize really strongly, like we say this every semester, and unfortunately, like as things happen, like a lot of people end up falling into this trap every semester. But you can say like, okay, I'm new to quantum computing. I haven't taken the course. I don't have any research experience yet. Let me go and read all of Nielsen and Chuang, and let me watch all 20 IBM lecture videos, and then let me start learning Qiskit. That's not really how I would approach it. If you're interested in getting into this field and you don't have any previous experience, the number one thing I recommend is, yes, learn like very basic quantum computing fundamentals, but then jump straight into, like a mini project or something like that. Like start coding things in Qiskit, because until you start applying all these facts, you're not going to be able to fully understand these topics. Quantum computing objectively is a lot harder than a lot of other types of computing to get into. And the only way to really understand some of it is to run code yourself. And so that's what we try to do. We try to put everyone in a position where you can always be actually running things and running code and getting results right away, because that's the number one way to learn and make progress. So yeah, don't go home and start reading a textbook from cover to cover. That's not how anyone who's like in the project today got into the project. Everyone who is in the project today and is still like active and has like made contributions to our papers has gotten into it by just saying, okay, here's something that needs to be worked on. I have no idea what any of it means. Let me read a couple papers, watch some YouTube videos, read some existing code, talk to people who are on the project about it, and boom, a couple of weeks later, you're writing new code. You know, that's a much better way to get into this field than reading a textbook, in my opinion. But yeah, I know I spend a lot of time like reiterating that, but a lot of people fall into the same trap every semester, and we want to make sure that you guys don't, because it's not the best use of your time. This is like the sort of flow chart to like decide whether you want to gravitate more towards like theory projects or hardware as we now have like an actual experimental project. And based on that, choose one of our areas of exploration. Oh yeah, I completely forgot to mention this. We have an entire bounty board of like dozens of tasks that no one has done yet that are meant for beginners. So if you want to like pick up something up right away, check out our bounty board. It's linked in our Discord in one of the quick links. It's on our OneDrive where we store all of our notes. So you can just jump straight in, pick something that sounds cool, and then start asking for resources about that. But yeah, once you like find something that you want to work on or gravitate towards, you can ask for like, what code should I read? What tutorial should I follow? What paper should I read? And ask questions. You know, our Discord is always there. Nothing is a stupid question. Even a question like, oh, what's a Hadamard gate? Or what's the difference between like a mixed state and pure state? We're open to any questions, even if it's not related to the project. So yeah, definitely feel free to drop your questions in the Discord. And then, yeah, once you like feel like you have the relevant background to like start thinking about like code to write, then we can like meet. And then like again, this is all under very close mentorship. We're not going to tell you, oh yeah, here's 5 papers, here's a task, read the papers, write some code, come back next week with your results. We don't operate like that at all. You know, we'll say, okay, here's some papers, here's a task, read the papers, you know, see if you get stuck, and then we'll like try and check on you constantly and make sure that everyone's making progress. But the point is, this is meant to be a very like smooth onboarding experience. So if there's ever anything that you need or you feel like you don't have enough resources, let us know right away. And yeah, you know, hopefully the goal is every semester, anyone who joins is able to write code that is permanently on the GitHub by the end of the semester. It's 100% feasible to do. Tons of people do it. You don't need background in quantum computing for it. It's just a matter of, you know, how much time can you put in? How much time do you want to put in? And yeah, that slide's not relevant. That's it. So I guess like if you guys are interested, I can just show like my #1 resource I recommend is this YouTube playlist. It's the second link in the resource flowchart. It's by John Watrous. He's at IBM still, I think. But yeah, he's like one of the most like successful people in the field. He posted these great videos, like 18 of them on quantum computing, and it even goes into quantum error correction. So if you want to like learn more about quantum computing, this is my #1 recommendation, more than like any other like textbook or articles. So yeah, definitely like watch. I would say like everyone should watch the first like 2-3 videos if you're new to quantum computing. But besides that, quantum computing is the sort of field where there's so much you can do that I can't really give anyone a resource of like, oh yeah, read this textbook cover to cover and you're done with learning quantum computing. It's a matter of what you want to get into. So like after this meeting, like I guess like we're pretty much done at this point. But if you guys want to like come up to any of the officers and ask us like, hey, I'm interested in this or that, feel free to, and we can guide you towards more specific resources. But there's not really any one shoe fits all or one size fits all sort of thing, besides this video series. And yeah, our GitHub is here, so it's public, it's open source. You can push code to it any time. We still have active pull requests that need to be completed. Yeah. But yeah, we have a ton of code, a ton of to-dos and things like that. But yeah, tons of stuff to work on. We're working on, I guess I can show one more thing if you don't think that we're doing anything interesting. We have a paper that's under the review process right now. They have a really long backlist, but yeah, this is entirely student-led. Everyone here is a student at Georgia Tech or was. These two are at Duke, but yeah, it's just like if you want to like read more about like the project, this paper, which is in the GitHub, tells you about like what functionalities we have and how we compare to other libraries. And, yeah, that's pretty much it. I know I like talked a lot, so if you have questions, feel free to ask now. You know, we have all of us officers, so Noah, me, Fien, and Elisa. You can come up to any of us and ask questions. or if you want to just like ask your question on the Discord, anytime, feel free to. We'll meet next week, same time, same place for our intro to quantum computing and intro to error correction. I think we're doing error correction next week. I forgot the exact schedule, but yeah, we're doing quantum computing, error correction, algorithms, and hardware workshops this semester. So yeah, next 2 weeks will be workshops. So if you want to come to those, definitely do. We'll have a recording for this meeting and all workshops on the Discord like posted. We have a YouTube channel where we keep all of these, but those will always be sent. I will say we don't record project meetings because usually project meetings are just us like breaking into groups and actually working on stuff and discussing individually. So if you want that experience, definitely either come to the Thursday meetings or fill out the when to meet so that you can show up to an alternate meeting time. But yeah, that's it. Thanks for coming. Grab snacks if there's anything left, and then hopefully see you next week in future wishes. Thank you.
Yeah. Right.
This is